In 2021, the revenue of the top 40 global mining companies, which represent a vast majority of the whole industry, amounted to some 925 billion US dollars. For these companies, their fleet of machinery and equipment is essential for daily function. When an excavator goes down, usually due to improper lubrication, it can cost the company between $20,000 and $50,000 per hour of yield. Lodgilube is a company based in Loveland, Colorado who sought out to solve this problem. They created the Lodgilube smart oil device that companies could embed in their lubricant systems that would take live data and pull fluid samples so the mining companies can perform preventative maintenance on their fleet to prevent any breakdowns and in turn save the company hundreds of thousands of dollars. The device works by opening a solenoid valve for a period of time to collect an 80 milliliter sample of the fluid running through the device into a small bottle that the mining company then sends off to a lab for testing. The goal of this project was to find a way to make sure the valve is open long enough to gather 80 milliliters of fluid each time, no matter the pressure, temperature, or fluid type. We were generously given a testing rig from Lodgilube that we renovated to work with their current device. The test cart can control temperature and pressure of working fluid and runs it through the smart oil device. The pressures and temperatures are measured using a pressure transducer and thermistor inside the smart oil device, both of those being connected to an Arduino. What is being shown here is the process of taking samples using the smart oil device on our rig. So as you can see, using the breakers, you turn on the motor that runs a gear pump that sends pressure into the system. What's not shown is an immersion heater inside the tank of fluid. And what you see here is the device actually taking the sample. As you can see, the small bottle filling up. The first equation you see here is Barr's equation, which we use to calculate viscosity. K, B', and theta are all constants calculated from fluid properties, while T is the fluid temperature. Underneath is the proprietary function we use to calculate the valve open time, which is a function of pressure and temperature. Due to issues with coding and sensors, we decided to use a timer relay, which you can see in the top right with the red box. We could set the time and the valve would open up for that certain amount of time. We use this for a lot of our testing. As you can see here, this is the viscosity curve calculated using Barr's equation that was shown earlier. This is very encouraging due to the fact that it mimics the shape of the viscosity curves that were found on the fluid data sheets that these companies conduct tests themselves, and this was encouraging also because it would give us an accurate viscosity reading. This next figure is the time to 80 milliliters versus the temperature, with the color varying with the pressure. As you can see, the temperature, there's no good trends with the temperature. However, when you look at the color scale, it's very clear that the pressure is the main input that affects the output, which is the time to 80 milliliters, which was calculated using the volumetric flow rate. As can be seen here in this figure, which is the volume over or under 80 milliliters versus temperature, there are a lot of data points outside the allowable limits of plus or minus 5 milliliters. Those points are mostly near the temperature extremes of 40 degrees Celsius and 100 degrees Celsius. This is bad news for our algorithm, as we need the result to be between the two thresholds. If the bottle overfills too much, the bottle will dislodge from the device. If the bottle is underfilled too much, the mining companies will not have enough sample fluid to send to the lab for testing and storage purposes. These problems could potentially be fixed by adding another term to the equation to account for the extremes. Overall, while we did not complete the deliverable we were shooting for, we came very close, as we currently have a promising Arduino code that calculates the opening time, but we just can't control the valve. The algorithm obviously has some flaws that could be worked out with more research and test data, but one thing that was quite successful was the viscosity formula used and the method of calculating those values. What we have achieved with this project is significantly more progress than what was made in one of Lodgilube's labs. We also took over 1,000 data points in various tests, which provide a great data set for future data analysis for Lodgilube. Like was stated earlier, a preliminary Arduino code is written and is very easily converted to a C++ code. Moving forward, the algorithm needs to be tested on different hydrocarbons as we only use Pegasus 805 motor oil. We want to extend a special thanks to some of our sponsors, starting with Bill Gillette, President and CEO of Logilube Smart Oil, who not only funded the project, but also assisted and guided us as we worked with his amazing product. Next, we want to thank Dr. Dan Olson, our faculty sponsor, for the continued support and advice as we navigated this project. Next, we want to thank Don Grove and Robin Bremer, who both offered invaluable technical and career advice as former mechanical engineers themselves. Lastly, we would like to thank everyone at the Colorado State University Energy Institute for letting us work in their facility and for all the help that various people gave us along the way. We would not have been able to have this amazing experience and opportunity without everybody involved. Thank you so much for watching.